All right, and here we are again for part two of the lecture for July 13th, 2016. This is classified as lecture 6 in the CENG 3306 lecture series. All right, now, so let's, for this portion of the lecture, we're going to get a bit more mathematical than we have in the previous portion, but that's okay. I hope you're ready to follow some fun and complex equations. Now, in the previous lectures, we have followed pretty linearly up through the first sections of the book, but now we are actually going to begin jumping around. In this course, we really don't follow the Hibbler book exactly. We really do jump around and make things work a bit differently than the author of the textbook organized things. So for this section, we are now jumping temporarily to 9.1 to 9.3. So we are going to be in the book 9.1 to 9.3. And the lesson objectives here, we want to solve for principal max and min normal stresses and the principal angle, and max in-plane shear stresses and the principal shear angle theta s. And we also want to learn how to solve for normal and shear stresses on different planes. So first let's review a bit about centric axial loaded members and the state of stress at different planes. We have gone through this before, but this is going to be the beginnings of our analysis. So we start with our state of stress here. And we have our cut plane, AA, going through at some angle theta. So we have our cut plane AA. So we have AA here. We have our X axis. We have our Y axis. And we are going to have a cut plane at a certain angle theta. Essentially what we want to do is we have our sigma x, our sigma y, well this is still sigma x over here, and we also have sigma y and sigma y, but we also have our shear stress, again simply all on the x related to the global xy plane. But what we wish to do is we wish to find these for any angle theta, and that's what we're going to do. We're going to need some equations to do that. Ta xy. So in other words, if we're given these, can we find the stress at any other angle? So previously I gave you the equation for finding the stress condition at various angles on a centric axially loaded member. But what if we have a general member, or in other words, any member? And if I give you simply sigma x, sigma y, and ta, can you find the stresses at any other angle given only this? In other words, if I give you the stresses in one position, can you find the stresses in another position? That's what we're trying to do today. So a brief review of the CAL member. Review of CAL member. So we have our CAL member. We have axial loads P on either end of this. P and P. We have our little stress point that we're trying to look at. And we have AA. Cut plane AA. Oh, that looks awful. That's not good. It would be nice if the cut plane actually went through our little stress element. A, A here. So a few things to keep in mind. One, while forces are vectors, stress is not. It is simply defined by the angle of the surface you are considering. It is not a vector. So, in other words, if we have this here, this element here, and we look at cut plane AA, A, and in a CAL member, you're going to have at the cut plane here, as drawn, sigma x. Sigma x would equal P over A, and sigma y would equal 0 at the default global x and y axes. However, if you look at a cut plane, this cut plane AA, and you have a different shear and normal stress, you end up with we still have the sigma x over here, but then on this surface here, we have a tau and a theta. We have a non-zero tau and a not theta, thinking my old Greek organization, a non-zero tau and sigma, like shown. All right, so let's see here. All right, moving on. And then also, it's important to note that tau max equals sigma max over 2 equals P over 2A for a CAL member. For a CAL member. Now, let's see. This is where we start really playing with trigonometry, and things are going to get really fun really quick. Stress transformation. So really what this is really just a bunch of terrible trig. And no, trigonometry is nobody except a high school math teacher's favorite, but it is what it is. So, stress transformation. Stress transformation. All right, so the first thing we're going to consider is that we have the global x and the global y, global x and global y, but we then have a shifted axis, the shifted x prime, and the shifted y prime axes. Let me make sure this thing is still recording because I'm super paranoid about that. And yes, we are, so let's keep going. We have a shifted x and a shifted y that we call x prime and y prime. And these are separated by an angle theta. This is offset by an angle theta. Now, let's see. So let me draw the same element from above. And here. And the book will also go through a very good derivation of this. Y and x. And then I'm going to have the hypotenuse of this triangle is going to be the AA line. Cut AA, A. And along this, we're going to have the x prime and y prime axes. So the x prime is here, x prime axis, and the y prime axis. And the y prime axes here. And this is separated by a certain angle theta. All right, and then let's see. So we first have our initial untransformed stresses that they're going to be on this side of the block. So we're going to have sigma x. We're going to have tau xy. Tau xy. And oh, that didn't turn out right. Tau xy, and then sigma y. Keep getting things erased. Sigma y, like shown. All right, and then up here, we're going to have sigma x prime, and let's see, we'd also have a sigma y prime. But actually, let's just keep it at for now. Actually, no, along here, we don't have a sigma y prime. We actually have the shear stress along the material, along the plane. So we have a normal stress and a shear stress along this plane. So along this plane. So the only things we have are the sigma x prime and the tau x prime y prime. Tau x prime y prime, like shown. All right, so let me work through a little bit of the trig here. Do this in blue. So let's see. Let's see here. This is going to be. Let's see. How might I? We basically need to solve for forces along the x prime axis. So we need to do quite a bit of trig to do this. So first thing to realize is that if you work through it, this is going to be theta, and this is going to be theta. And then, let's see, what else? We're going to have this be, the area here is dA sine theta. dA sine theta. So if we're doing forces, the forces here will be dA sine theta times tau xy. The area on this piece is going to be, if we're talking a little dA, little differential element, but it's dA cosine theta. All right, not dwelling too much on the trig if I can avoid it, but this is also theta and theta and theta. And if we work through the differentiation, the derivation, if we start by saying the sum of forces along the x prime axis must be equal to 0. Oh, excuse me, sorry. Along the x prime axis must be equal to 0. Essentially what we're going to do is we are going to do a balance of forces. We can't do a balance of stresses. We instead have to do a balance of forces and also take into account their areas that they act upon. So the, let's see, essentially what I'm calling dA, I guess I didn't quite label that properly, this area along the hypotenuse is dA here. And the force here is going to be sigma x dA. This is going to be tau x prime y prime dA. This is going to be tau xy dA sine theta, because that's the area this thing acts upon. Tau x, this one would be act over tau xy dA cosine theta, because that's what this area is, and so on and so on. This would be sigma x. This will produce a force of sigma x dA cosine theta. So all we're going to do to get forces, is we're going to take all of these forces and all these stresses and multiply them by the areas they act upon. So this will equal sigma x prime dA, sigma x prime dA. Look here. This is, so we're summing forces along the x prime axes. The, let's see, the sigma x prime dA, well, sigma x prime is this, acting this way, and we just multiply it by dA, the area here, the little differential element area, to get the total force along the x prime axis, minus sigma x dA cosine theta times cosine theta. One of the cosine thetas comes from turning the stress into a force. The other term comes from turning the force into getting the component of it along the x prime axis. And same idea for tau xy, the two tau xy's. So let's just, it's the same idea. All we're doing is we're taking the components and working through the trig. So tau xy dA cosine theta sine theta, and then minus sigma y dA sine theta times sine theta, minus tau xy dA sine theta cosine theta. And I probably should have put parentheses around all of these if I was along the second ones for clarity, but oh well. Okay, the dA's all cancel out, and what we end up with is, we combine these together, I end up with sigma x prime is equal to sigma x cosine squared theta plus sigma y sine squared theta plus 2 tau xy cosine theta sine theta. And I am going to designate this in further derivations as equation 1. Basically, we're going to need to get, today we're just doing a nightmarish derivation. So we're going to need a whole series of equations. So I'm going to call this equation 1. Okay. So next I am going to use a little bit of trigonometry again. Some oh joy, trig identities. Remember this stuff? Lovely. Trig identities. Trig identities. In the main one I'm using are the double angle identities. Joy. So the trig identities I'm going to use are, if you remember the double angle identities, cosine squared theta equals 1/2 times 1 plus cosine of 2 theta. Sine squared theta equals 1/2 of 1 minus cosine of 2 theta. And sine theta cosine theta equals 1/2 sine of 2 theta. This is essentially allowing us to get rid of our cosine squareds and sine squareds. Alright, so moving along. If I substitute these into equation 1, so sub trig identities into equation 1. And we will get that sigma x prime equals sigma x over 2 times 1 plus the cosine of 2 theta plus sigma y over 2 times 1 minus the cosine of 2 theta plus tau xy sine of 2 theta. Or I can finally get something really useful and something that appears in the textbook, sigma x prime, this is sort of a classical expression of this, sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 cosine 2 theta plus tau xy sine 2 theta. And this is equation 9-1 in the textbook. But for my lesson today, I'm going to call this equation 2. We have many equations today. This is equation 2. Equation 2. Now, let's see, what's next? So next I need to do I did a summation of forces in the x prime direction. Next I'm going to do a summation of forces in the y prime direction. Taking the forces and multiplying by their areas, dAs and things like that. I don't necessarily feel like the need to work all the way through it, but I will show the result you get when you do that. So if we do a summation of forces along the y prime direction equals 0, we will get that tau x prime y prime equals negative sigma x, minus sigma x minus sigma y over 2 times the sine of 2 theta plus, that looks really bad, plus tau xy cosine of 2 theta, and we are going to call this equation 3. It's equation 9-2 in the Hebler book. This is our equation 3. And let's see, for equation 9-3 in the textbook, if we use the theta positive for counterclockwise and positive tension for theta positive is, if we define theta positive as counterclockwise, sigma positive is tension, and tau positive coordinate system, we can also find that sigma y prime equals sigma x plus sigma y over 2 minus sigma x minus sigma y over 2 cosine 2 theta minus tau xy sine 2 theta. And this is equation 9-3 in the book. Another one, and this will be another one of our critical equations to work with. So what we now have is 3 equations that, notice what we have. The inputs to these equations are, so this just reminder, 9-1 in the book, 9-2, and 9-3. The inputs to these equations are the x and y and tau, sigma x, sigma y, and tau xy in any coordinate system of your choosing. Then the sigma x prime, the sigma y prime, and the tau x prime y prime are the outputs of these equations, and those are the shear and normal stresses along any other angle. So next, I want to find what we call the principal stresses. So let us find the principal stresses, which we refer to as sigma 1 and sigma 2. Principal stresses sigma 1 and sigma 2. So we have found that we now know how to find the shear and normal stresses at any plane of rotation. But what if I wish to know the maximum? What if I want to know the maximum values? So these will occur when sigma x prime is max or min. Well, I know how to find the max or min. I took calculus. So d sigma x prime over d theta equals -2 times sigma x minus sigma y over 2 times the sine of 2 theta p plus 2 tau xy cosine of 2 theta p, and the tan of 2 theta p equals tau xy over sigma x minus sigma y over 2 and this is going to be equation 4 here. Or sigma p, the angle, the principal angle, is 1/2 times the inverse tangent of tau xy over sigma x minus sigma y over 2. Here. And this here is more critical. Very important. This is equation 9-4. 9-4, where theta p is the angle of the principal plane with counterclockwise rotation. And the tangent you know from trigonometry that the tangent repeats itself every 180 degrees. Every 180 degrees. Therefore, principal axes, or principal planes, I should say, principal planes are 90 degrees apart, or pi over 2 radians. Planes are 90 degrees apart. These are 90 degrees apart. So this thing repeats every this thing repeats every 180, but we have the 2 theta p, and also we have the max or min. So it occurs at every they repeat. The principal planes occur every 90 degrees. Okay, now we need to do some substitution. If I substitute equation 4 into equation 2 into 2, I can actually get an expression for the maximum for the principal stresses. Sigma 1 comma sigma 2 equals sigma x plus sigma y over 2 plus or minus the square root of sigma x minus sigma y over 2 plus tau xy squared. And this will be equation 5 for our derivation purposes. This is equation 5, or it's equation 9-5 in the Hibbeler. And let's see here. Again, sigma 1 is going to be the max in-plane normal stress. And sigma 2 is going to be the minimum in plane normal stress. Normal stress. And thus, we can have sigma x minus sigma y over 2 tau xy. And so we have this here and this here. And our angle here is 2 theta prime. And we have, this is a geometric relationship, a showing of the geometric relationship between all of these. Sigma x minus sigma y over 2 squared plus tau xy squared, just done via the Pythagorean theorem. Next, if we substitute 4 into 3, substitute 4 into 3, four into 3, we will find, if you work through that, you actually find that on the principal planes, tau x prime y prime is equal to 0. Therefore, tau equals 0 on principal planes. So if you have a, in other words, on a principal plane, it is a state of pure normal stress. There is no shear stress whatsoever. So y prime, x prime here, we have no shear stress. We have only pure liberated normal stress, nothing else. So you'd have sigma 1, maybe perhaps like this, and sigma 2, perhaps like this. Okay, so that's how you find your maximum in-plane normal stress. But what if you want the maximum shear stress? What if you want the maximum shear stress? So let's find that. Maximum in-plane shear stress. So what if we want to know at what angle the maximum shear stress occurs at? Tau max. Well, we're going to do the same kind of derivative and setting it equal to 0. So d tau prime that should be tau x prime y prime. Tau x prime y prime over d theta equals 0 equals negative 2 sigma x minus sigma y, taking the derivative, over 2 times the cosine of 2 theta s. Theta s will be the angle that we call the angle of maximum shear stress. Let's see, minus 2 tau xy sine of 2, or sine of theta s here. So, continuing through there, we'll find that the tangent of 2 theta s equals negative sigma x minus sigma y over 2 over tau xy and this will be equation 6. for our lecture today, or it's also equation 9-6 in the Hilbert book. And solving for sigma s, we end up with it's 1/2 times the inverse tangent of negative sigma x minus sigma y over 2 over tau xy. And that's a very mutated tau, so I'm going to fix that. Over tau xy. And let me make sure we're still recording. Yes, indeed we are. This lecture is going to go very long, but that's okay. All right. Note. Since 2 theta p and 2 theta s are negative reciprocals, they are 90 degrees apart. Reciprocals, they are 90 degrees apart. Therefore, theta s is 45 degrees from theta p. Theta p. So in other words, if we drew this out, so say we have the x-axis here, and then here, let's say we had an x prime and a y prime. Well, actually, let me show in blue first. Say we have the theta prime here, the principal theta. Well, then the another x prime, y prime, the location of the maximum shear stress will be 45 degrees from that. X prime, y prime will be 45 degrees from here. 45 degrees. And the stress condition there, the stress block on this plane is going to be as follows. And we'll see where sigma average comes from shortly. Let me show in red the actual stresses. So the first thing I'm obviously going to have is tau max, and the same tau max opposite here. And then the normal stresses are all the same value. Writing on top of my writing, which is never a good proper form, but oh well. Sigma AVG, sigma AVG, sigma average. We will get that shortly. Okay. Well, actually, I guess I won't necessarily go through that derivation. Essentially, sigma average, we'll see that more when we get to more circle. But essentially, the sigma average is the average normal stress across the entire plane. Okay, so finally, I want to get an expression for the actual value of the maximum shear stress. We don't have that yet. We only have the angle. So if I substitute this angle back into our shear stress as a function of theta, substitute 6 into 3, substitute equation 6 into equation 3, we will get the following. We will get that tau x prime y prime equals tau max equals the square root of sigma x minus sigma y over 2 plus tau xy squared. if you're noticing that these equations look a lot like the equations of a circle, that's no coincidence. And you'll see that when we get to more circle. This is equation 9-7 in the Hibbler book. So this is kind of important, so box that, really critical equation. Or another expression of this, so this allows us to get the tau max directly from the initial untransformed stresses. Alternately, we could say tau max, if we already have the principal stresses and we just want the maximum shear stress, is sigma 1 minus sigma 2 over 2. In other words, the maximum shear stress is going to be equal to the average of the two principal normal stresses. Whew. And we're not done yet. I have a little bit more of derivation and then a few examples to work through. First, let me make sure we're still recording. And indeed we are. 40 minutes, not bad for that kind of derivation. Okay, so finally a little bit more theory. What's known as stress invariants, or these quantities are stress invariant. There are some stress invariant quantities. Stress invariant, in other words, the total amount of stress is conserved on any plane. So we don't make stress disappear, we just transform it. When you work through the equations, you'll find that sigma x plus sigma y equals sigma 1 plus sigma 2, or any sigma x prime plus sigma y prime. They're all the same. So therefore, the sum of stresses on perpendicular planes, that's perpendicular, is constant for a given loaded. For a given loading. For a given loading. Actually, we'll see this, the average stress thing here, sorry. Or, finally, if I substitute 6 into 2, I get an expression for the average stress. And sigma average, the average stress on any plane is simply sigma x plus sigma y over 2. That's the average normal stress in a system. Alright, so I want to work through one example of transforming stress, and I think then that will do it for today. Okay, so let me do that. And there are plenty more examples in the book for you to consider. So, example 1. Let us say we have a stress block in the following condition. So this is given, this stress block is given, we have this state of stress. All of these are given, like here. Notice the way shear stress is drawn, it is negative. So tau xy is, I'm just listing this as 500 psi for now. Sigma x is actually going to be in compression. Sigma x is 1400 psi. And sigma y is in tension. Equals 1000 psi. So this thing is simultaneously in compression and tension. Alright, so we have this, we're given this nonsense. And we want to find determine principal stresses, and find, and show, I should say show, not find, show orientation on which they act. Orientation on which they act. In other words, we're looking for sigma 1, sigma 2, and theta p. Okay? So, let's see. Sigma x. So we are given, again, we know that sigma x, so solution, we know that sigma x is negative 1400 psi. I'm just putting in negative because it's compression. Sigma y is going to be equal to positive 1000 psi because it's in tension. And tau xy is negative 500 psi. Not because it's in compression or tension, but simply because it's going opposite to our standard sign convention of positive shear stress. So, let us apply this formula. The principal planes are where normal stress is at max and tau equals 0. Where normal stress is max and tau equals 0. So we're going to use the formula, this formula here, sigma 1 comma sigma 2 equals sigma x plus sigma y, and this is just this problem is just plug and chug, plus the square root of sigma x minus sigma y over 2 squared plus tau xy squared, or substituting in numbers, we can say negative 1400 plus 1000 over 2. Oh, and this should say plus or minus, not just plus. Sorry about that. Plus or minus. Plus or minus the square root of negative 1400 minus 1000 over 2 squared plus negative 500 squared. Now, let me just go ahead and clearly label these. This term here, you notice, is sigma average, the average stress, and this term here is tau max. So we could very easily get the tau max as well. So moving along, if we work through this, we will find that this is negative 200 plus or minus 1300. So the average normal stress is negative 200 psi, and the tau max is going to be 1300 psi. So we find then that sigma 1 is 1100 psi tension, and sigma 2 is equal to negative 1500 psi, which is 1500 psi compression. T, if you can't read my terrible handwriting. And then theta p is equal to 1/2 the inverse tangent of negative 500 over negative 1200 equals 11.3 degrees counterclockwise. And this comes from just the same formula you've had earlier. We could have also used theta p equals the inverse tangent of tau xy over sigma x minus sigma y over 2. But that's neither here nor there. So I want to then draw this, the orientation. So let's see, we're going to have a stress block like this. This is the original x-axis. Then we have the shifted x-axis, x prime and y prime. And here okay, that keeps erasing. No, we're good. Okay. And the angle here, the theta p, counterclockwise positive, is 11.3 degrees. And then showing the orientations. So do make sure you know how to do this. Might ask this on an exam, you never know. Sigma 2 equals 1500 psi, and sigma 1 is 1100 psi. This in compression, this in tension. And we can double check, and we can actually use our stress invariants to check our numbers. Well, we can't prove that we have the right number. We can't prove that we have the right numbers by doing this, but we can potentially disprove it if we got it wrong. So just a quick check. Sigma x plus sigma y is negative 400 psi. And what do you know? Sigma 1 plus sigma 2 is also negative 400 psi. So that might be useful. Alright, and we could work through more examples, but it's all going to be a fairly straightforward implementation of this. Once you have the equations are can be rather difficult to determine, but you know, actually, let's see, let's look at the time. Yeah, I think I can do one more example. Let me do one more example. So let me do one more example here. Let me do 2 examples total. So example 2. So let us start with a stress block. We are given all of this. So we have a stress, I know this can be difficult, so I want to make sure to give you plenty of examples. So say we have sigma y equals 1000 psi, like so, and sigma x equals 1400 psi. And we know that tau xy equals 500 psi. So now let's look at shear. We looked at normal stress before. Let's in this one look at shear. So I want to find tau max and theta s. So let's say that sigma y equals 1000 psi and sigma x equals negative 1400 psi. And tau xy equals negative 500 psi. So this came directly from this. Tau xy is negative 500 because its opposite are positive sign convention. Sigma x is negative because it's clearly in compression, and sigma y is positive because it's clearly in tension. Okay. So it's actually the same exact stress condition as before. Well, yes, it's actually the same exact stress condition as before. We're just working with we're just finding different quantities. So, solution. Well, let's say that tau max equals sigma 1 minus sigma 2 over 2, and this is equal to the square root of sigma x minus sigma y over 2 squared plus tau xy squared. Oh, and yeah, that's good. And this is equal then, is equal to 1100 psi minus a negative 1500 psi over 2 equals 1300 psi. Alright, I'm working along and I'm writing kind of big. I guess I'm in a little bit of a hurry. Sigma s equals theta p plus 45 degrees. So we could just use our theta p and get it, but let's say we could also do 1/2 the inverse tangent of sigma x minus sigma y over 2 all of this. Let me erase this bracket temporarily. All of this over tau xy. And if you plug that in, you will get 56.3 degrees. So finally, let us calculate sigma average equals sigma x. Oh, that's a tau, not a sigma. Sigma x plus sigma y over 2 equals, that's going to equal negative 200 psi or 200 psi compression. So if I show the stress block here at the maximum shear angle, we're going to have the following stress condition. Well, first of all, let's find the angle here. Let's list the angle. 11.3 degrees plus 45 degrees equals 56.3 degrees. Or here, if we have, let's say, 1300 psi, and then we would have 1300 psi in shear, and we are drawing it as positive shear because that's what our equations indicate, and we're drawing it in an orientation compatible with our sign convention for positive shear. And notice I am drawing on all sides. We have the same sigma average. Sigma equals negative 200 psi. It's the same sigma average on all sides. Sigma equals, oh my goodness, that looks pretty bad. Sigma equals negative 200 psi. And that's the complete solution. Alright, if you have any questions on that, please let me know. Hopefully that should give you enough for your homework over this stuff. And feel free to contact me whenever is convenient. Best way is again by email. Wish you good luck on this. Hopefully that illuminates a few things. Again, read your textbook for a also a very thorough derivation. And as always, let's see, there will be homework due on Thursday evening as well, so do make sure to keep up with it, make sure to keep watching the lectures, review as needed. Again, I recommend that you take notes of these lectures as you watch, just like you would in a regular classroom lecture, just to learn this in the most effective way possible. That will work. We will have a lecture on Thursday, none of course on Friday, but then we will be back up again on Monday. So let me know if you need any assistance, and as always, thank you.